Hey there, Huskies. Welcome to section 1.10, and I hope we're getting our heads wrapped around how things are working here at Reno High, and if not, then maybe this video is going to find you and help solidify some of those things that you're trying to get done. But 110 today is going to be about some modeling questions, and primarily modeling questions turned out to be kind of word problems. I know that may have turned off some of you, and you probably shut the video off at this time. But I'm going to try and simplify these word problem kind of questions down to ultimately be focused on things that, like a general idea of what they're basically asking for. Now, before we end up doing any of those kind of word problems that are coming down the pike, we're going to try a couple of review questions just to remind ourselves on what kind of things you should have learned in previous sections with Coach Leesman. And that would be, first, let's talk about the inverse. Inverse meaning to switch the x and y, which will end up with x is equal to y cubed plus 7. And then you isolate the y again, so this ultimately should be x minus 7 is equal to y cubed, or the cubed root of x minus 7 is equal to y. And ultimately, this one will not need a plus or minus on it because the root is of an odd power. I'm going to skip the idea of the example of a function that shows as an inverse, but then it really does feed down in here into these review questions about what we're going to be talking about today. If you would like to model the volume of a rectangular solid, what type of polynomial would you be likely make the best choice? Now, if you're going to make something that's going to be based on volume, you'd really want to be thinking about something in that rectangular solid that would be an idea of length and width and height. So it would make sense that the idea would be written in a cubic sense of idea, because you'd be dealing with the dimension of each kind, whatever it happens to be, in terms of an x component, and that x component in the end, once it would be all foiled together, would be an x cubed concept. Okay, so, and this really leads us into some of the real life kind of situations or functions that we're going to see down below, that when you see things like volume and you see things like surface area, you're going to be really thinking of a function that's ultimately related to that. Now, this next part says, think of a real life situation that could be modeled by each individual type of function. And one might say, let's say we're talking about something linear, and I'm just going to draw a linear graph going straight down like this. This might actually be your bank account as it is in the COVID pandemic. It is just going down and down and down because you don't have the chance to work. Okay, work is not something that's working out for you, so your bank account gets done. So ultimately, you'd hope for a, Trump stimulus, and you get a little kind of kick out of that bad boy. So try to make it something that's reasonable based on what's going on. How about this one, a quadratic? If I was taking Coach Leesman on a cliff, I would want to push him off the cliff, and ultimately he would fall towards the ground based on a quadratic graph in terms of acceleration and velocity. So quadratic graphs, thinking about something that's x squared. In this particular case, I picked a negative x squared because the parabola is upside down. Exponential, if you haven't been watching the news lately, you haven't caught anything that's been going on about COVID. COVID in terms of exponential. I saw one just the other day that was incredibly, it made me laugh. This one was about the number of unemployment and how many new unemployment cases were being done each individual week. Well, since March, compared all the way through September, the graph has been doing this. This is an exponential decay kind of problem. Now, at the same rate, the amount of COVID cases that are going down while all these people are going back to work has been going up like this. And you'd think that maybe the two graphs would start to understand one another, and we'd find that nice little happy medium somewhere in the middle here. Now, just the concepts that are there, just about modeling some stuff. We're going to talk about some simple modeling kinds of questions that you might run into when it comes to doing some questions tonight. Now, again, they are word problems, But the idea is that you should be able to read some kind of word problem and glimmer some kind of piece of information from it. Now, ultimately, here's a good piece of information that you are going to inherit $45,000. But unfortunately, somebody probably died to give you that money. But the stipulation is that your grandmother said for the first year you have to put it in 2 different investments. She's probably giving you in the background, oh, you got to diversify, like that. And then you got to put it into 2 different accounts. Now, it doesn't really make a whole lot of sense. You'd probably put it all in the 6% interest account in the first place and just get as much money as you can. But if there was some kind of idea about volatility between these 2 different accounts, it would make sense. Now, if you were going to calculate the interest that you were going to make on those 2 functions, first off, you would probably calculate the interest of making it in the 6% account. And interest is basically you put in a certain amount of money into the bank, an X amount of money, and you multiply it by 0.06, which is the interest, and it gives you the interest that comes out. It's pretty straightforward. Nothing really exciting about that. Now, the problem is that when you go to count the interest in the 5% account, and usually this is the way most of these modeling questions work out, is that there are 2 equations that you have to intermingle with one another, is that this particular account, you can't put every single amount of money in there, and you wouldn't want to put in a Y amount. That doesn't make any sense. You'd want to put in whatever amount you didn't put into the 6% account. So that would be $45,000 minus the actual deposit that you put in the 5% account. So you have to kind of think ahead when you're doing these kind of problems, and you would multiply this by 5% as well. Now, if you wanted a total amount of interest between these 2 accounts, you would ultimately take these 2 values on either side, and you would just add them up, and you would get the total interest amount as written as a function. It says write the function in the amount of money invested in the 5% account at 5%. Ooh, see, I did that backwards. See, I wasn't reading the function of the money invested at the 5%. This one would be, sorry, I'm going to change this slightly. It really doesn't make a whole lot of difference. This is the 5%, this is the 6%. And so forth. We would end up adding a total 5% account, which would be 0.05x added to, and this one would be distributed as 0.06 multiplied by 45,000 minus 0.06x. Like that, and, oh no, I did that wrong. Sorry. That would be 0.06 times 45,000. Sorry, guys. 45,000 minus x. And ultimately, you could write the whole thing in terms of x, distribute and so forth, and you'd end up having a function of the amount of interest that you would make based on if you put money in the 5% account first. Now, what this particular question really does for us is it kind of highlights the idea that there's really a first equation and a second equation, and they somehow work together to ultimately write an equation about either, in this case, total interest or something else down the line. Now, most of these kind of questions end up dealing with like an interest kind of concept like that, or maybe in this example too, they might be a geometric modeling kind of idea about the surface area of a cylinder. Now, when you read these, you want to read them carefully and really start thinking about what your 2 equations are and how those 2 equations are going to work together. So a typical 12-ounce soda can, and I'm thinking that a soda can is a cylinder, so that might be helpful, has a volume. Now, as soon as you see these things right here, you're thinking, okay, volume is probably the first equation that it's associated with. Well, 22 cubic inches of volume of the original concept is based on the volume of a cylinder, and the volume of a cylinder is pi radius squared times height. Now I'm just going to write it like that so I can get some idea of what's going on, but this particular equation seems relatively put forward, but it has an R and an H in it. Now it says express the surface area of that can. Well, if I was talking about the surface area of it in square inches as a function of its radius, we want to find the surface area in relation to its radius. Well, the surface area is pi radius squared, 2 of them, because you got the bottom and the top, and then you end up doing pi times the diameter, so the circumference of the bottom times the height. Now, here's the biggest problem. the surface area formula that you're basically dealing with right here only wants it in terms of r. So you're like, wait a second, I've only got to write it in terms of r, but it's got d's and it got h's in it. So what you've got to do is find a way, or like, okay, this part of the formula seems like it's all right. The pi is okay. The d would be probably 2r. But the problem is the h. You're like, I don't know what h really is. And that's where the first equation really ends up giving you an opportunity as a substituter to help you figure out what should go in for that h value. So ultimately, you solve this particular equation for h. And if I divided that part off, I get 22 over pi radius squared. And I could put that particular idea right here, 22 over pi radius squared, as a straight substituter for h. And then I could simplify the question down so that it's about surface area in terms of r. The pi's would cancel one another. The 22 in that would make 44. They get an r to cancel. And you'd end up with 2 pi r squared plus 44 divided by 44 over r. And you'd ultimately have that equation right there, which would be the surface area of any type of soda can with 22 cubic inches of volume and its radius and what it would turn out in terms of its surface area. Now, the reason why they do these kind of questions like this is because ultimately a manufacturing company would be really interested in knowing what the surface area of those cans is going to end up being based on its volume that it can take, so that in the manufacturing process you could figure out how much aluminum you would need in terms of to make this, and the process in terms of manufacturing. It's a graph is all it really boils down to. Now, this cell phone plan one, I think the problem has some issues with it. It says AT&T is providing a $59 cost with unlimited texting, and Verizon plan offers you a cost of $49 a month with 1,000 allowable texts, and then beyond that there would be a specific cost to the actual things. Now, if you were talking about somebody, you'd be like, what choice would you pick? Would you pick AT&T or would you pick Verizon? Well, it's really circumstantial. If you're one of those people that texts a ton, then you would pick AT&T. But if you're one of those people that is a minimal texter over the monthly idea, then you would do the Verizon account, and you basically are a hermit. I don't know what the idea is. Now, it says here how many months of text would actually have the cell phone accounts actually be to make them equal. Now, the problem with this is that there is no value for how much the texts would be afterwards, but ultimately you would have $59 on one side, $49 plus the number of the cost based on what the actual cell phone is, and you'd basically set the two plans equal to find out when they would cross, when they would benefit. So it's often cases where you have one idea comparing to another idea, and you're trying to find out when those two particular graphs cross. It's not a very good question. It needs some modifications. Okay. Now, again, they might also ask you about maximization kind of question as well too. That's what example number 4 is about here. What would be the maximum volume of a box modeled by the following volume concept? Now, I would say that that volume concept actually probably came from two different equations that were working together to get this maximization question. This is like that maximized surface area question. Now, what they're trying to do is find a maximum to this particular idea. And if you think about this particular graph, it's going to be a cubic function, because if you substituted or GCF'd this guy inside here, you would end up with a cubic function, and ultimately it's going to have some kind of shape that's based on a cubic function. Now, your calculator does a really good job maximizing these particular functions, so I'm going to kind of model what that would look like so you could get the idea. All I did was put the f of x, or the v of x in this case, in your calculator based on one variable, and that's why you'd have to write it based on one variable. And then I would go straight to graph. Now I'm going to zoom 6 this so that we can kind of start to explore how we might have to adjust the graph. And you'll probably see the graph go whoosh off the deal, and then I think it barely comes back and so forth. So I'm just going to remind you of some techniques that you have in your repertoire, like maybe your window. I want to see that maximum. It's up way high, so maybe 250, and I'll scale it by 10. And let me look at that graph again so I can get a better idea. I'd stay away from things like zoom fit because they have a tendency to actually flatten the graph. Hey, look at that. Gee, you did a good job. Way to go. Now, here's the real question. How are we going to find the maximization of this particular graph? Now, to find that maximization, you're thinking that this particular region right up here at the top is the local maximum. That's going to be the x value, and that's what this is graphing. It's really graphing the dimension of the box based on the volume of the box. So think about the bottom being based on x is the dimension along the box values, and this represents the volume of the box. So there's a maximization point at the top. Your calculator can do this by a calculate maximum, and then it asks you from some boundaries that you'd be looking for. So I'm going to pick a left-hand boundary and a right-hand boundary, and then I'm going to guess to what it actually is, and it'll give me a coordinate, in this case, that the maximum is listed at 2.33, repeating, and 200 and, man, what is that? It's pretty hard to tell. 283? I'm going to go with that. 283.25. Now, what the heck does this particular thing mean? Well, again, this is standing in for x. They're basically saying the dimension of one of the sides is 2.3, and then the other dimensions are so forth, and it would give you a maximum volume in terms of y, that the maximum volume you could possibly make in that box would be this size. Now, again, you're thinking, how does that relate to anything in real life? I don't know, man. Finding the maximum volume of something that would be manufactured could be a very key idea. I mean, you just don't guess on what size the box needs to be. Okay. Next, same kind of question based on area. So an area question is modeled by these two ideas, and I think these are probably coming from two different equations too. One would be the area formula for a rectangle. That's what they're plugging into, which is base times height. And maybe the top one is based on perimeter, that the perimeter around the object is 100. It's supposed to be 100, and that ends up being that the perimeter is going to be 100 minus x for one dimension and so forth. It's a perimeter concept that's going inside right here. Now, this is what the end result of it is. Now, the question is, what would be the maximum shape that would maximize the area? Now, if you're really kind of thinking about ahead of that, you're like, oh, okay, I got a rectangle, I've got the big fat rectangle, I don't know. You got to, like, which one's going to maximize it? And I think most of us are probably thinking maybe it's got something to do with the square. Well, let's check that out. If I took that function right there and I plugged it into my y equals, and I tried this question out a second time, x, and then times 100 minus x, and I took a look at what that function did in terms of a zoom 6. Let's see if we can get a graph out of this bad boy. And it's off the charts again. Maybe I might have to do a window. Probably expand the y first. Let's get it up to 150. Scale by 5s. Maybe we want the x's to go further from 0 to 10 by 1s. Let's see if I get the graph to pull off something. Oops, I'm not quite there yet. I think I got to go a little bit higher. I'm going to check my graph, make sure I did things right. Yeah. Let's go to the window again and make this go a little bit higher till we get something that looks a little bit more reasonable. Let's see, does it come out? And I don't know what it's doing. It should end up x minus 100. Yeah, I don't know why this particular graph is not graphing a parabola for a maximum. It should be an upside down parabola. Maybe I'm just not getting high enough. I'm getting crazy now. That's 5,000. It looks linear. What is wrong with that? I'm going to pause and check this out. All right, so I figured out what my problem was, and that was the fact that I wasn't thinking about the domain that could be going in there between 0 and 100. So I scaled it to 100. You'll see I got a graph that looks like that. There's the other side of that parabola. Now we're probably going to want to change the window to go really high. So it's way higher than 900. Let's think it's like, I don't know, 3,000. And we'll scale it by 50s. That means it should be relatively doable. Let's see what we got here. Oh, look at that parabola. It's so beautiful. All right, so we've got ourselves a parabola shape. The question is, where's the maximum at? Same kind of idea. Second calc, we can maximize this. And ultimately, we'd get a left-hand boundary and a right-hand boundary on either side of this. And my expectation, as you guys were saying, the fact that it might be a square, seems reasonable that the actual answer is 50 and 2,500. And that makes sense that the dimensions of the sides should be 50, and a maximized area that you're going to generate out of it is 2,500 square units. All right? So the key here is look at the problems themselves and make a decision about what the two problems are either trying to put together to make into one, or how they're really asking you to maximize something, and your graphing calculator can really make the best deal for you. Try the 1.10 worksheet and come to the class with some good questions, and we'd be more than happy to help you.